Cheng Chin from the city of Chicago, talking about many molecules. Thank you, Chen. The floor is yours.
So sorry for the delay. Can you all hear me? Okay, very good. Okay, so I'm going to tell you about this how we study some of the process in this quantum regime. So in the University of Chicago, we try to study this quantum simulation, and we are inspired by models from different physics disciplines, lens matter, cosmology, and even recently jet physics. But today I'll be more focusing on some of the models we can try to be predicted how the chemical reaction will occur in the many body regime. So there'll be two systems I'll be talking about. Okay. My title mostly on the first one, okay, and by also some interesting result on the both Fermi mixture I will be talking about. So the first one is based on the molecular BEC, okay, then how the reaction going from atom to molecules, okay, can be modified in the many body environment. Okay. And I've been talking about a few topics. This about 4 years effort, and this is not 5-year effort. I try to finish integrated 9-year effort within kind of 30 minutes. It's not that difficult, right? All right. So the way we create molecular BEC, we're using phase bar resonance. So and compared to something which I did as a postdoc, we're able to convert atomic BEC into thermal molecules. This time you can convert it into molecular BEC. Okay. We are doing the 2-dimensional 2D regime, okay, and then this will go to much lower temperature in 10 nanokelvin. The interest in this observation, like you go to lower temperature, you see a more better stability. So this molecule can now have a lifetime more than kind of 50 milliseconds, and enough to do a lot of interesting physics. All right. So what do we expect the chemistry to be different when you go to the quantum regime? Right here, we have atom molecule. They're all occupied a single quantum state. So compared to conventional chemistry, right? So it looks like this should start working. So let me use this. This should be the next pointer. All right. Okay. Compared to conventional chemistry, who I will not talk too much about. Okay. When atom occupy one field, okay, forms a field, matter wave field. Molecule forms another field and then react. Okay. In the most fundamental way, this is a conference about fundamental process. So in the kind of quantum regime, think about that's how the fields are mixed. Okay, the interaction Hamiltonian can be written as essentially that the simplest case would be the kind of a 3-way mixing of matter waves. So what are the new features of this such kind of interaction? If you put it into the computer, then you can see there's if you start with 100% atoms. Now it's a different kind of this mean field prediction will be this line going down. Okay, you just convert everything to molecules. Okay, and assuming bring them to resonance. And then, but this full quantum calculation seems to suggest some kind of damping, but it's not a true damping. It just appear to be like a kind of damp oscillation, but there's a lot of correlation entanglement build up. And at the end, I'll tell you about how we can see this correlation and the entanglement. And this is what we see in the experiment. So T equal to 0, we had atomic BEC with a few 10,000 atoms. And then within a couple of milliseconds, we can see this fast kind of this coupling between the two species. And then later it shows indeed some coherent oscillations. And then if you look at these oscillations, now you realize that this oscillation, the frequency is not a simple kind of Rabier oscillation, but this is a nonlinear field mixing. So the higher the field strength, then the stronger the mixing, the oscillation frequency will be. It's a nonlinear process. Okay. All right. So looking at this oscillation frequency as a function of the particle size, okay, we're able to compare different theoretical models. The simplest model, how you couple atom and molecule based on the two-body model, where 2 atoms are annihilated and converted into one molecule. Okay. But when we see the oscillation frequency as a function of atom number, okay, what we see is a much better agreement with this magenta line, which is based on the kind of 3-body coupling. Right here, because right on resonance, Okay, the 3-body process can be stronger than 2-body because there's an additional. You can see you have the 3 operator here and the 3 operator here, or 2 operator here, totally 5 of them. Compare that to G2, then essentially it's additional kind of density, right? 5A dagger 5A, there's additional density.
Sorry,
So in the presence of high density, you have a stronger, yes.
just what's the scattering length?
The scattering for the molecules or for atoms?
Well,
Okay. This is on resonance. So this scattering for atoms, infinity. Okay. Scattering for molecules, that is turns out to be 200 Bohr, but it's small compared to this phase-bar coupling strength. Phase-bar coupling strength in this case, in our case, about 10 kilohertz.
is there an imaginary part to the molecule scattering length?
We have a lifetime of about 15 milliseconds. That's the most I can say. So probably on the order of kind of 10 hertz. All right. So this coupling strength in the 3-body coupling, in this you can that will give you a much stronger kind of dependency. The difference between 2 and 3-body is how this coupling strength depends on the density of the sample. In the 3-body process, there's stronger dependence. All right. This is what we published 2 years ago. Now we're talking about our more recent result. Okay, so here's the Bose enhancement that we expect when the field is occupied by many particles. Another important aspect of this nonlinear mixing of matter wave fields, okay, is so-called phase matching. In a way, similar to how, okay, I'm sorry, there's something missing. So I'm going to show. Now imagine in your mind. So this is for optics. You can convert red photon into blue photons in a nonlinear medium. For atoms, okay, I have a second figure, but somehow disappear. But essentially, it looks similar. It's on a matter wave with 2 atoms. Okay, they are matter waves, okay, like this. And now they totally now there's a nonlinear process, which is the phase-bar resonance. Compare 2 atoms into 1 molecules. Okay. And in principle, this is governed by the same kind of Hamiltonian that you annihilate kind of 2 red photons and create 1 blue photon. Here, we annihilate 2 atoms, create 1 molecule. Okay. So this is the same process supposedly should apply to matter waves. Okay. So, no, it's not. Okay, here's one. So the idea is that this, if these are governed by the same process, supposedly in this kind of reaction process, you should also see the phase matching. What this means that the phase of the atoms should be connected to the phase of the molecules. And we expect the molecular phase should be proportional to 2 times the atomic phase. And there may be a small phase constant, okay, that need to be checked. All right, so can we see such a phase? It can be shown this phase is the one that will drive the transition, whether you go from atom to molecule or molecule back to atoms, a reaction phase. How do you do such kind of a phase test? If you want to measure the phase, you need to prepare, you do some kind of interference experiment, compare this interfere 2 kind of wave functions. So the original idea is the following. How about we just cut the BEC into 2 halves? Okay. And then the right-hand side impose a phase, theta A on the right-hand side. And then I pair atom into molecules. Then in this case, then the molecule on the right-hand side should acquire a phase, theta M. And we can check whether theta M is 2 times theta A. Immediately you can see this very interesting problem if you think about it in terms of this many body physics. Because if it turns out theta A is pi, now on the right hand side is a sign flip. But once you double it, now the sign flip disappears. So you see these two order parameters, these 2 wave functions, they reflect different symmetry. On the experiment side, what we did is we are doing the following. We apply instead of using just apply a phase jump on only one side, we try to apply a kind of a standing wave. The standing wave will kind of introduce a phase modulation on the atoms. And then we can try to pair atoms and see how much phase modulations is the same or is enhanced. Okay, so to prepare for that, we first showed that our atomic BEC and molecular BEC indeed they are phase coherent. So we perform a series of this diffraction experiment. okay, can do the so-called this capacitor direct diffraction and Bragg diffraction. Such kind of diffraction on atom have been kind of realized for decades, and people use that this diffraction to perform precision measurement based on atoms. Okay. Similarly, we can see the diffraction experiment on atoms. What you see is an atom with zero momentum be diffracted to plus 2h bar k and minus 2h bar k. Because whenever you turn on the lattice, now you essentially virtually absorb a photon, emit a photon. There's a two momentum recoil transfer. A molecule will also see the same thing. Molecular BEC diffracted to plus 2h bar k, minus 2h bar k. But because molecules are twice as massive, so the displacement is a factor 2 smaller. And you can see the coherent oscillation based on capacitor direct diffraction. And Bragg diffraction, we send this standing wave with a kind of relative frequency difference. So it can preferentially kind of couple your atom or the BEC to another state, become a kind of two-level system. So can describe by the spin kind of dynamics. So you can see on atoms and molecules, you can see Rabi oscillation between just two states. All right. Now, let's go to the main experiment. So what we do is I want to introduce a phase modulation on atoms and then pair them. If the modulation we apply is a phi A, A refers to atoms, and then at the pairing, want to measure how large is phi M, okay, where the molecule also be modulated by the same amount or supposedly twice as large. Okay. In this spin language, you can see whenever you apply this oscillation, you apply this diffraction, you couple your atom into a superposition, one with zero momentum, the other one final momentum. Now, the linear process going to take the whole wave function and square. So you can imagine now 3 terms. Okay, what that means is that zero momentum atom can pair into zero momentum molecules. Final momentum atom will pair into final momentum molecule will be 4 times the recoil. Okay, that'll be 4IKX. But they also the kind of interference term. Okay, that will be zero atom with zero momentum can also pair with a atom with a finite momentum. So the cross term, okay, is cross term is shown in here. This is zero momentum. This is a final momentum. Okay, there's a second harmonic generation. The 2 atoms with the same momentum can pair into a molecule with twice the momentum because of momentum conservation. Or 2 atoms with zero momentum pair into molecule with zero momentum. But there's also a slightly different process called some frequency generation. It's atoms in different momentum state can be paired into molecules with a momentum that equal to the sum of the 2 original atoms. So in a spin language, you have spin 1/2 atom, and pair them becomes spin 1. Okay, you have a 1 minus 1, 1 0, and 1 1. Okay, so you can see on molecules, we see kind of molecule being scattered into 3 different momentum, 0, 2, and 4. Okay, when atoms are prepared in kind of superposition state 0 and 2. Another thing that's very interesting, but now you realize this equation, the linear field equation, is that the molecular wave function proportional atomic wave function square. So therefore, if you try to look at the molecular population, it will naturally show you the second order correlation of the atoms. Because the molecular wave function proportional atomic wave function square. So if you look at the molecule with zero momentum, then you're actually looking at second order correlation function of the atoms. Okay. If you look at molecules with 4 units of momentum, then that means you're looking at atom with 2 units of momentum. Okay. The 2 atom with 2 units of momentum will give you 4 units of momentum. But if you look at the cross term, okay, now the atom with a 0 momentum pair with another atom with 2 units of momentum, then get M2. 2 means 2 units of momentum. But this is a factor 2 because the cross term, okay, will give you a 2, and you square it to get a population, you get a factor 4. Okay. So this ratio 1, 4, and 1 is already beyond classical expectation. Right? Classically, if you throw 2 coins, the kind of cross term 0, 1, and 1, 0, you cannot be more than 50%. All right, so let's first talk about this how from this spin oscillation, this molecular BEC, okay, how that can tell us about the phase. Okay. So looking at this oscillation, it's not surprising when you can determine determine the phase pretty well. Okay? And the phase modulation we apply to the atoms can be linked to the population of the atoms and different molecular state. So here's the first result on the phase doubling. Okay, you can work on the math. Okay, when you see this Rabi oscillation on the atoms, then we can determine what is the mean phase modulation on the atoms. Okay, that will be the horizontal axis. And perform this measurement independently. Okay, based on the same perform the experiment, we perform the measurement of the atoms. Then we determine this phase on the atoms. And then when we pair these atoms into molecules, okay, we can measure the phase on the molecules. And phase molecule given by that formula, okay, which we show the derivation in our paper on the supplement. Anyway, so this is a simple math. We can determine how much we modulate the atoms, how much you modulate the phase of the atom, how much you modulate the phase of the molecules. And you can see horizontally go from 0 to pi over 2. Okay, is a modular pi over 2. In the vertical direction, 0 to pi. Okay. So we have get a very good agreement. This essentially this is the ratio is 2. Okay, but our accuracy now is good enough. Okay, yeah, earlier I didn't need to show the kind of residual. Earlier our error bar is larger, but recently we improved the error bar to a kind of to a percent level. We started to see a tiny deviation. Okay, this tiny deviation on the order only a few degrees. Okay, if you get the residual, compare the phase of the molecule subtracted by phase of the atom multiplied by 2. This residual, it turns out, is there. There's a small contribution at the level, kind of few percent. Okay, that's actually due to these two processes. Second harmonic generation and the sum harmonic generation, they are not, they don't have exactly the same strength. Okay, yeah, but this is a detail I can explain to you more. Okay, because when you try to pair two particles with a relative momentum, the process is of resonance. Our phase bar resonance is very narrow, only a few kilohertz. But this process, okay, is all resonant by kind of 2 recall energy, kind of 5 kilohertz and so on. Okay, but that's a small correction. All right, so this is a confirmation, except for that small details. Now you see a clear kind of phase doubling of a matter wave when atoms appear into molecules. Now, lastly, let me address this entanglement generation. As I mentioned earlier, from the molecular population, you can essentially directly show, reveal this second order correlation of the atoms. Then we can ask, when the 2 atoms appear into molecules, are these molecules really in the product state? Okay, all right. So each atom is a spinner. Okay, when they appear into molecule, it turns out that if you, as a function of time, we see the Rabi oscillation, we can evaluate that this different kind of entanglement weakness. One that's particularly easy for us to access is so-called parity. Okay, this parity, which is sigma z1, sigma z2. 1 and 2 refer to the 2 atoms. That turns out all we had to do is measure the molecular population. If this number is outside the range of 0 and 1, that means non-classical. Okay, and what we see, it goes down to minus 0.15 with an error bar on the order of 0.02. Okay, so around here, okay, that's actually here is where we had a pi over 2 pulse on the atoms. So atom going to the equators and then pair them. Okay. And then because of this extra fatal 4 due to both symmetry and so on, now we create a non-separable state. And we show that they are not separable. So in principle, they are entangled. What kind of entanglement do we create? So to test the nature of this entanglement, we introduce a kind of, for 2 atoms, this is simple, we introduce a Bell state basis. It can evaluate entanglement weakness, okay, how well the system overlap with any one of the 4 Bell states. Okay, and these are the formulas. We plug in the formula, we can evaluate this as the entanglement weakness. For entanglement weakness, anything below 0 is classical, anything above 0 is this non-classical or is entangled. Okay. And once you evaluate all the weakness, it can reconstruct the molecular wave function and show that the molecular wave function is a superposition of these 2 entangled states. As long as the weakness is a positive, okay, then you'll give you the this negative parity and this positive weakness. Okay, but when we go to 0, then it's an equal superposition of C minus and phi plus. It turns out it becomes a product state. In our case, we get a stronger strongest entanglement after this time, which is pi over 2 powers on the atoms, 3 pi over 2 powers on the atoms, 5 pi over 2 powers on the atoms. Okay, that summarizes the first part. Okay, these are coming in these 2 papers showing the both enhancement and also this phase matching, phase doubling, and also entanglement generation, which is just on the visible. All right, I'm going to just move on to the second topic. Okay, but this now, so here this is just a single component, kind of this BEC of a bosonic atom CGM. In our second experiment, well, we have this separate apparatus. We are looking at a mixture of boson with fermion, and remind ourselves this when you go to lower and lower temperature, boson will condense, so the size become pretty small. But fermion, even go to just the same temperature, pull down fermion down to about this 10 nanokelvin, you can see the size doesn't really shrink that much because there's a Pauli exclusion principle. And this from in situ image, okay, we can take this image of this particle immediately within kind of a few tenths of microseconds. So essentially, the particles do not have time to move during that time. So you can see atoms. The BEC is embedded in the Fermi gas. Okay. For now on, we use a blue color for the BEC and a red color for the Fermi gas. The Fermi gas is much larger. That also implies a much higher kind of Fermi energy compared to the chemical potential of the boson. And you can also compare these two, one with a attractive interaction between the 2 species. So therefore, there's enhancement of fermionic density here. The other one, you have a kind of suppression when there's a repulsive interaction between the 2 species. Okay, for today's talk, I'm more focused in this regime where the CGM scattering is small. That means a stable CGM BEC. But within this range, the lithium CGM interaction is divergent. Okay, then we can try to explore the kind of a resonant behavior of this both Fermi mixture. Okay. Right, and these collaborations done in our group and also in University of Heidelberg in this Matthias Weidermüller school already many years ago. We understand the interaction parameter very well. Okay, so near the resonance, what we did earlier based on a thermal gas is how we are able to identify ephemeral resonance. Okay, and we actually found multiple ephemeral resonance. We can show the geometric scaling of the ephemeral resonance. They're all based on thermal gas. The thermal gas, when temperature, when the scattering large enough, okay, the 2 CGM and 1 lithium atom, they can form a 3-body bound state. Now, in the many-body regime, so the more recent work, in the many-body regime, one particular thing that's different is that we don't need to go to resonance. Even away from resonance, you can see some effect, because even the 3-body process can modify the interaction between particles. There's ephemeral potential. Okay, just like in any phase bar resonance, you can make the interaction repulsive on one side, attractive on the other side. Okay, but in the many-body regime, the discussion more in terms of this how this one species is embedded in another species. Okay. If these 2 particles have very different energy scale, in our case, that is the case because the CGM is heavy, with heavy boson embedded in the light fermion. So we can talk about how the one species can induce a modification of the second species. And there are many examples in physics. Okay. Particularly, that's RKKY is relevant to us because that is something that's an interaction between these impurities that can be mediated by fermions. So now we have 2 scenarios. Near the resonance, we have something called ephemeral potential, especially because we have heavy boson light fermion. It has been proposed and be kind of suggested that ephemeral potential can also be think of as a kind of effective potential between 2 heavy bosons. The light fermion doing most of the work based on this one Oppenheimer approximation. And the other scenario is RKKY scenario. Okay, that in the many-body regime, now you also have this heavy boson being treated as impurities. and their interaction can be mediated by this by the presence of Fermi gas. And right there, the relevant energy scale is the Fermi length scale. Okay, the RKKY potential looks like this, is a KFR. But for ephemeral potential, the relevant energy scale is a van der Waals length that determines the range of the potential. So how will these two pictures kind of come together? If you try to do the same experiment in the many body regime, you have both a Fermi length scale as well as this ephemeral potential. Okay, or the potential is 3-body bound state. Are they differences? Are they the same things? Are they connected to each other like a BCS crossover? Is a smooth transition, or is something happening in the middle? All right, so that's what we want to explore, how we can tune this atomic both Fermi scatteredness, kind of going from the weak coupling regime in RKKY limit into toward the ephemeral potential and see something happen. Oh, turns out it's not a smooth transition. Okay, it's not a smooth transition going in between these two limits. All right, so in the weak coupling regime, let's summarize what we did earlier. We can try to measure how the scattering is influenced by RKKY mechanism. Okay, and we show that there is this RKKY indeed works, that it kind of modify the interaction between heavy bosons when heavy bosons are embedded in the Fermi gas. That's a weak coupling regime. Okay, now we also studied the sound propagation. It showed that there's suppression of sound become unstable when the fermion this density gets higher or the both fermion interaction gets stronger. Okay, what we see, the sound velocity being fully suppressed, the sound is quenched. But what's that wasn't expected, that wasn't understood at that time, is that somehow near the resonance zero, okay, near the resonance, the sound propagation kind of revived. Okay, we totally didn't expect that. Okay, we've seen a stable, healthy sound propagation when the system runs on resonance. So we continue to study this. Now this is coming from most recent publication just a few months ago. Okay, so first of all, we try to really study the kind of dispersion. Okay, so what you're showing here is a 1/over scattering length. So that means phase bar resonance here. Okay, and then the reason studies her dispersion that provide a kind of a sensitive probe into the stability of the BEC and see how the sound is quenched, is suppressed, okay, and somehow recovers. Okay, and look at the imaginary part of this response. Now we see a clear resonance in the presence of Fermi gas. Red one is 100% fermion, blue one 50% fermion, and black is 25% fermion. Okay. In the present, without the fermion, everything is gone. There's not a single features in this range without the fermion. So everything is induced by the fermion. Okay, but it leads to a clear, sharp resonance. And that resonance is not the ephemeral resonance, not a phase bar resonance, but somewhere else. Okay. Okay. So that means so why is that this a new resonance? Why is what happened? So from the dispersion, it looks like the system become unstable. That means the BEC essentially is in the left in some kind of metastable state. So the next thing we try to look at is that this in the RKKY regime, we look at the BEC, everything stable, okay. But once you go to this new resonance, this unexpected resonance, now the BEC quickly become unstable. What you see, our feed, the blue one shows a kind of fraction of the BEC, and the red one is an excitation into the kind of thermal gas. But if we jump to the phase bar resonance in this many body system, turns out the phase bar resonance the system is more stable than this mediated resonance. Okay, so this is the interesting. Now I show you another resonance. Sorry. Here. Again, 0 is the phase bar resonance. The dotted line is ephemeral resonance measured at this thermal field, thermal gas, okay, normal gas. Now, these three plots show the behavior of the CGM BEC. Now I see a strong kind of strong decay at this position, which is roughly about -1. -1 meaning the scatteringness of about 1,000, -1,000 Bohr. It is a new location. And BEC decays and accompanied with a kind of heating. Okay, you can see this particle kind of be heated to the wind. Okay. Not consistent with our kind of dispersion measurement. Okay, the system loses stability, sound is quenched, and then there's a strong kind of this population transfer from the BEC to final momentum state. That's heating. All right. And that's a position. But if you look at a fermion, okay, this position, this fermion turns out is not at this position. Okay, this fermion doesn't change that much. The fermion has shown another weaker resonance, okay, at a different location. So it looks like this is one resonance position for cesium, for the boson, another one for the fermion. So we try to do a more extensive research to figure out what exactly is going on. How do we go from the classical regime where you see a one ephemeral resonance, and now a phase bar resonance, ephemeral resonance, and now going to the many body regime, now everything seems to be shifted and also by different amount. Okay, so here's a temperature kind of scan. 366 nanokelvin, that's roughly our 1 Fermi energy. Okay, and going down to 15 nanokelvin, now this lower temperature, you have almost pure this atomic BEC and highly degenerate Fermi gas. Okay, and then you can see how this resonance be shifted. Okay, yeah, the figure be squashed. It looks like this is not a very strong signal, but this is a lot. Okay, this actually. And then see how much does it influence the Fermi gas. So to make a long story short, we compile everything together. At high temperature, okay, we can recover what we measured before, the phase bar resonance, ephemeral resonance. These are coming from 2-body and 3-body process. So I drew this cartoon to show above this line, okay, you have this phase bar resonance induced by pairing of lithium and cesium. Ephemeral resonance due to the kind of emergent of 3-body bound state. That's everything above this critical temperature. But once you go below critical temperature into the many body regime, okay, then we have we have something that's more complicated. Okay, what we have is if you try to approach the resonance, we start with a kind of regular gas. Okay, this both Fermi mixture and so on, atom. Okay, the first thing we see is something like a resonance on the bosons, but fermion doesn't seem to be affected that much. It looks like the fermion is mediating the resonance in a way similar to RKKY, but this is no longer in the RKKY regime because the system is strongly interacting. And then we start to see the resonance on the lithium. Okay, and beyond that, okay, we think we are more into the ephemeral regime. Okay. So the original ephemeral resonance that is kind of 3-body pairing seem to be kind of separate into 2 steps. Okay, first of all, the RKKY has some weird interaction that we can measure with the BEC side and sound velocity and so on. When you increase this interaction, metal attraction stronger and stronger, it looks like the first thing we see is a fermion-mediated pairing of bosons. But fermion, they are not bound. And then we made it even stronger. Now we go from this 2-body state into a kind of 3-body state where we get close to our familiar this ephemeral cesium to lithium trimers. Okay, yeah, it looks like now becomes a 2-step process because now cesium and lithium respond to the interaction differently. All right, so for this part, I'd like to conclude. Okay, in the weak coupling regime, we see the RKKY potential that consistent with the prediction. Finally, in this intermediate regime, we found a new resonance, what we call a fermion-mediated resonance. Okay, where they cannot apply RKKY is also questionable whether to apply ephemeral when this KF becomes important. Right. So what we see the resonance position for this fermion-mediated resonance occur at KFA roughly equal to -0.5. Okay. Theoretical prediction is -2.4, but depends on the mass ratio. Okay. This is very interesting. You can see that when the mass ratio is very, very large, okay, now this resonance can be shifted, okay, closer to the weak coupling regime. And based on the evidence we have, it looks like in the many body regime, the process is like a 2-step process. First, lithium can mediate interaction between cesium. When that interaction is strong enough, it can lead to the pairing. Okay, and medium play a role more like a kind of a, essentially kind of a just a mediate interaction. Okay, but then cesium is also paired into the cesium at a slightly different position. Okay. And that position depends on the temperature and likely depends on all the kind of many body energy scale. All right, so this is the network semi group members, and the lithium cesium was done by this 3 graduate students, and the cesium molecular BEC done by this 2 graduate students and our postdoc. Okay. Yeah, thank you.
Time for question, please. Please, Jose.
The original RKKY model is an indirect spin-to-spin interaction, even when the spins are not interacting. So these intermediate resonances you find could be seen as like a 3-body resonance or?
Right. So in the right here, I was more like kind of spin this kind of RKKY potential. Okay. It just show the characteristic kind of their oscillation and the length scale is given by Fermi momentum. Okay. But going from here, that's if you start from this RKKY picture and try to push to larger and larger scattering length. Okay. And then the prediction at some point, this potential will become deeper, but then also become shallower again. So actually, it wasn't clear whether it can support a bound state. It will happen in a strong coupling regime. Okay, so from this calculation from Tillman and also from Nishida, I believe, they suggest that if you try to in the strong coupling regime, this potential can at most support only one bound state. Okay, but their calculation cannot go to resonance.
But it would be a 3-body bounce.
Right, because then the 3-body bounce rate will take over. So this comparison, indeed, this is from this RKKY extrapolated into this strong interaction regime when KFA is sufficiently large. Okay, and that's a prediction. Right. So our understanding is that this RKKY potential is also ephemeral potential. How these two should be added, or should this maybe a new formula in the we should use in the intermediate regime? I actually don't know. Okay, but it looks like there's a bounce state emerging before we see the ephemeral.
Please.
Yeah, I was a little confused by some aspects of your first part of your talk. So you had an atomic BEC at unitarity. First of all, I thought that's supposed to be very unstable and immediately goes away. So I don't understand how you're doing experiments with a BEC of atoms. Also, if there is a BEC of atoms and molecules, the question of miscibility comes in. Are they miscible or not?
Okay, yeah, so I didn't make this clear. Let me go to the beginning, how we prepare atom molecules. All right, so we either have an atomic BEC or molecular BEC. Okay. So to create a molecular BEC, we use a phase virus and convert atoms to molecules, and then we'll blow atoms away. Okay. So for all the kind of molecular data is based on pure simple molecules. Okay. So say the data here. So here will be 100% atomic BEC. Here's 100% molecular BEC. Okay. So at least so far the mixture.
And you have some field oscillating in addition? I didn't understand that either.
Oh yeah, okay, that is so you can see they do coexist for kind of a couple of milliseconds. Okay, but then afterwards, for the phase phase measurement, now we blow atoms away. So for a couple of milliseconds, they can. So this is for the first couple of milliseconds, we see how atom number decays, how molecule number increases. You need to have a coexistence to see the coherent oscillation between two species. But later, when we prepare the molecular BEC, we blow atoms away. Yes.
Johannes.
Related to that, I was wondering, you were talking about the phases.
Yes.
And I was wondering the energy, let's say, that is released when atoms form a molecule.
Yes.
How does that come into play with these phases?
Yes.
I guess you kind of want to minimize that energy, but it's probably the energy that's being released. Yeah.
Okay. All right. So when you do the diffraction, so we perform some kind of phase modulation on the atoms. Okay. So that will lead to kind of into energy transfer, and that can be seen from this fraction of the atoms in the kind of a 2H bar K state. So atom will be, initial BEC will be here, and some population will be transferred to this state. Okay, and the energy for 2H bar K, the energy is 4 recoil. Now, when pair them, if atom has a 4 recoil energy, now I pair them together, molecule have 8 recoil energy. The mass is twice as large. So then you can see these are the molecules, okay, that acquire 2 units of momentum from the atom because of pairing. So atom in the superposition of 0 and 2, you can see the image on the lower part is 0, and this atom with 2 units angular momentum. But when you pair them, the molecule can have a 0, 2, or 4 because you kind of expand the square. Okay, so molecule 0, 2, and 4. So momentum is still conserved. Okay, but just have a different kind of fraction of the molecule going to 0 momentum, 2 momentum, and 4 momentum.
I was talking about the binding energy of the molecule itself. I mean, you probably tune it to, because you're on resonance to
Yes.
essentially 0.
Yes.
But I was just wondering if what is 0, yeah, and
Yeah,
how you tune a little bit, so you have some binding energy that comes into play. How what effect does it have?
So experimentally, we control magnetic field about 0.5 milligauss. So the energy difference between them will be on the order of about probably like 200, 300 hertz. And that's very small compared to recoil energy. Recoil energy here is 4 kilohertz.
Okay.
Right. So that amount is essentially negligible. And second, because we are doing the interfering experiment, so we're looking at the population here and there. So that only compare the molecules right here. Yeah. So only essentially compare the relative phase between here and here. Okay, so the binding energy doesn't really play a role. This is a relative phase between this modulated, unmodulated atoms. Compare the relative phase between the modulated, unmodulated molecules. Okay. So the energy kind of detuning will be a common factor that will be eliminated. So this is essential idea. If you apply some kind of phase modulation on the atoms, and how much would the phase of the molecule be modulated? So when pair atom into molecules, and also pair this atom into molecules, now you can measure the relative phase, okay? And this can be done by the diffraction experiment, and also measure the relative phase from the diffraction experiment of the molecules.
So how deep is, so you actually compare here 2 condensate, right? You explain all this that there is a condensate one and you just make. But in the practice, you actually make it in the standing waves. I just wonder how this is close to this nonlinear crystal, like periodically poles that makes the phase matching. How this does this has anything to do with the necessity of introducing
the phase matching condition? They will say the momentum conservation will be the result of phase matching. Right. If you think about this, for instance, this theta A is something that's proportional to position. Okay. Then the derivative of the theta respect to x tell you the momentum. Okay. Then you pair them. Suppose the momentum should be twice as large. You pair 2 atoms into 1 molecules. Therefore, it's not surprising the phase of the molecule should be twice as large. Right. So in this experiment, what we do is that when we provide this modulation, there's a phase modulation on the atom like this. Okay, this is how much the phase is modulated as a function of position x. Now I pair them. So expectation is that the phase modulation on the molecule should also be a factor 2 larger. Okay. So to show that this the phase doubling works, so with this we do the diffraction experiment, we can show that the diffraction efficiency. So this when atom being diffracted to 0 momentum and the 2K momentum, okay, the population of atom in the population here these are the atoms with zero momentum. In the beginning, 100% zero momentum. Okay, and the Bragg scattering will see the Rabi oscillate between 0 and 2h bar k. Okay. And then the population exactly with kind of this depends on the phase modulation. So this is a phi A, the how much you provide the modulation can be linked to this essentially the kind of rotation angle of this Bragg vector. Okay. So from the oscillation, we determine how much we perform the phase modulation on the atoms. Also from the oscillation, we determine how much this molecule being phase modulated. Okay, so from here, we determine phi A. Here, we determine phi M. In the plot one against the other one.
I was wondering when you talk about the female physics,
Yes.
is this always referring to the strongest bound female state? Or because there is this hierarchy, right? Of
Yes.
female states.
Right.
far do
This
you
is the
see-
first one. Yeah,
This is the
first
first
female
one.
state.
So do you have a chance of seeing also effects of the
Right.
lower, the higher ones?
In another broader this phase bar resonance, we can see 3.
Okay.
This is a narrow resonance. Our temperature not quite low enough to see the second one. Yeah.
Any more questions? Well, okay, you.
Oh, yeah, just refer to the second part of the talk. As someone who just learned the STEMAC, what would be the order parameter of these Fermi mediated resonance?
Okay, that would be that should be the field of this CGM2. Okay. Right, so BEC of CGM and BEC of CGM2, they are 2 different order parameters. So one way to demonstrate that, I think I mentioned here. To show that BEC of atoms, BEC of molecule are different. You can think about if you apply a kind of symmetry transformation, introduce the EI phi A, then the molecule should have a twice the phase. Okay, that means if you apply a pi phase shift on the atoms, on the molecule, there's nothing with the 2 pi phase shift. Okay, this will show that they respect different symmetries.
Any more questions? If not, let's think again, Cheng Chin, please.